Hi everyone, welcome to part 5 of lecture 11. And in this lecture, I will give you some exercise about the independent exponential random variables. That is important because you will use the exponential random variables in some in some other classes, in some other lectures, in features. That's why that's important to understand some properties of the exponential random variables, okay? So I believe that that's a good time to show this kind of properties. So let's say we are given two random variables, x and y, and they are independent exponential random variable with the parameters, the rate, the lambda x and lambda y. So, and let's calculate the probability of x will be less than or equal to y. So how can I calculate this probability? First of all, let's visualize that one, that ask probability. So we have the x and y random variables, and that is the joint PDF actually. So just imagine that this upper region actually shows the region x is less than y, right? So the thing I need to do is to calculate the probability of this region. In other words, to calculate the volume under that region, okay, for the each pair fall within that region. So how can I do that? It is simply, I know I can calculate the joint PDF of that two random variables. So like fx y xy, because they are independent, that is equal to the marginal PDF of two random variables, right? And I know the marginal PDF of that random variables because they are the exponential random variables. Remember that the corresponding PDF is lambda times e to the minus lambda x. Okay, so simply I can first of all I can multiply the individual marginal PDF of that two random variables, and that will give me the joint PDF, right? And after that, after finding the joint PDF, I can integrate that joint PDF for the so I can integrate the joint PDF over the domain, and that domain will satisfy this condition: x is less than or less than y. So let's start. The joint PDF of x and y is equal to the marginal PDF of the product of the marginal PDF of the random variables, right? And which is equal to lambda x times lambda y times e to the minus lambda x plus lambda y, right? Because that's coming from the lambda times e to the minus lambda x, and that for the x random variable, the lambda is lambda x times e to the minus lambda x and x, and times lambda y e to the lambda y times y. Okay, so that the product of these two marginal PDF will give me that one. As I said, I need to integrate this joint PDF over the domain that will satisfy this condition that x is less than y, x is less than y. But let me clear that one. How can I specify the limits of the random variables? Because I have to specify the limit of the integrals, right? That will be two integration, and that will be based on the y and x. But what will be the limit of that random variables? So the first things, there are two ways, or how can I calculate the volume in that region, under that region? Simply, I can do something like that, right? Like imagine that I'm creating some small, tiny rectangular here. So actually, that is the basic logic behind the integration. And I will calculate the area of that rectangular, and then I will create another one. I will create another one. So I will fill that region with that small, tiny, the rectangular, and I will sum up the area of that rectangular will give me the total area or volume under that region, right? So Imagine that I will create that rectangular for all possible region here. That means the y, like let's say, by the way, that region is the boundless because x can go to infinite. So there will the y, I mean that region will continue until infinite, okay, towards to the up. So that's mean I need to evaluate that integration for the y variables from 0 to infinite, right? But for the x1, for the x1, I cannot start from the 0, right? Because if I start from something here in this region, the x will not be less than y. That's why at least I have to start from this point, and this in that point, that is the line shows the y is equal to x, right? So that will be my lowest limit for that one. The y will be here. Y will start from the here and will go to infinite. But if I start from here, the x will not be x will not be less than or y. So the y should start from at least from this point for that rectangular. For that rectangular, the y should start from that one. That for that rectangular, y should start from that point. Okay, that shouldn't be lower than this one. Okay, y shouldn't start from this region. And these two guys, a common point, which is y is equal to x. So that's mean the y, the lower limit of y should be x. So that's why the inner integration should start from the x and goes to the infinite. Okay, and let's look at the x. So I will create the rectangular for any possible x values, right? The rectangular will start from, let's say, from here, like from 0 to infinite, right? So the x will start from 0 to infinite, and y will start from 0. So y will start from x and will go to the infinite. And that's why the outer integration will start from 0 to infinite, okay? And the inner integration is with respect to dy. That's why it starts from the x, and the integration, the first integration, the outer integration is based on x, and x will start from 0, and that will go to the infinite. Okay. So the first one is based on the y, right? And the lambda x is not based on y. And also e to the minus lambda x is not based on y. So they can go outside the first integration, the inner integration. And I can rewrite that part as the integration of lambda x e to the minus lambda xx. And this guy will be lambda y e to the minus lambda y dy dx. Okay. First, I can do this part. Okay, and this is the integration of this term is minus e to the minus lambda yy. And I just need to evaluate this guy for the infinite and the x values. Okay, so remember the antiderivative of this one should be this one, because if I derivative of that one, the minus lambda will be here. So minus times minus will be positive, and that will be lambda times e to the minus lambda yy. So I will get this one. So if I evaluate this term for this point for the infinite, so remember that is based on y. So the y will be infinite and x. If it will be infinite, that will be 0 minus. If it is an x, that will be minus e to the lambda y x. right? So that will be e to the lambda y x. Okay. And also I have similar things here, which is e to the minus lambda xx, so which is e to the minus lambda xx. So I can rewrite this two multiplication as e to the minus lambda x plus lambda y x. Okay, and I have this term lambda x here. Again, I need to take the antiderivative of this one, so I need to integrate that guy. So that will be simply the lambda x divided by minus lambda x plus lambda y times e to the minus lambda x lambda y. And I need to evaluate this guy for the infinite and the 0. And that is based on x. If I gave the infinite, that will be 0. If I gave the infinite to the x, that this whole term will be 0, so 0 minus. If I gave 0, so that guy will be 1, and I will end up with this one. So that will be minus lambda x divided by lambda x plus lambda y, right? So that will be, the results will be lambda x divided by lambda x plus lambda y. So that is interesting, right? Because if we have two exponential independent random variables, the probability of one random variables is less than another is the rate of the random variables, which is that should be that is asked to be less than another one. The rate of that random variables divided by the total rate. Okay, so that is the interesting results of two independent exponential random variables. What was the question? The question was the probability of x is less than y. So if you have any questions, something like that, you need to remember that one. The results should be rate of x divided by rate of x plus rate of y. Okay. So also, another way is to integrate first. Let me show on the graph and let me clear that one. We can create rectangular in another way, which is something like that, right? Right, that. So in this case, I need to evaluate the integration for y, and the y will start from 0 to infinite, right? And x will start from the 0, but that will go to the y, right? Am I right? Let me check that one. It will start from 0 and it will go to the y. Let me check. If x goes beyond to y, that will be in that region. That's why x will start from 0, but that cannot be greater than y. So upper limit will be y, right? Because if that's not the case, the rectangular will be something like that. Okay, so this region will not satisfy this condition. That's why the upper limit of x should be y. So if you prefer to do the same thing for this way, in this way, I need to integrate the joint PDF for based on the dx and dy, and in this case, in this way, the limits of x will be between 0 and y. Okay, so the rest of the things is same with the previous one. So here the lambda y and e to the minus lambda y is not depends on x, so they can go outside the integration. So that will create this part, and the inner part will be integration of lambda x times e to the minus lambda x. dx and dy, and the limits will be 0 and y. So if I get the integration of this guy, that will be minus e to the minus lambda xx, and that will be evaluated for y and 0. And the results will be 1 minus e to the minus lambda x y, because so if you gave the let me give you y here, so that will be minus e minus lambda x y minus minus 1, right? Because if I gave the 0 here, that will be 1, and there is a minus here, the minus 1. So this guy will be 1 minus e to the minus lambda x y. Okay. So I can do the multiplication here. That will be lambda y times e to the minus lambda y minus lambda y e to the minus lambda y times e to the minus lambda xy. So I will just distribute this coefficients. And then I can split that integration based on that subtraction. That will be lambda y e to the minus lambda y dy minus the integration of lambda y e to the minus lambda x lambda y dy. So if I get if you can integrate this part, or you can just focus on what is that, which is the exponential distribution with the parameters lambda y. So that is the total area under that distribution. So that is equal to 1, or you can just get the integration, or take the integration of that guy, which will be simply the minus e to the minus lambda y, and you can just evaluate as that one for the infinite and 0. So that will be 0 minus e to the minus lambda y 0. So that will be 0 minus 1. That will be 1. Okay, so this guy will be 1. And we know that one. That is, or we can just do that. So the integration of that one is lambda y divided by or minus divided by lambda x plus, lambda x plus lambda y. That should be evaluated for the infinite and 0. If I infinite, there is a e to the minus lambda x plus lambda y, okay, and y. So if I evaluate for the infinite, that will be 0 minus 0 minus minus lambda y divided by lambda x plus lambda y. So that will be, the results will be lambda y divided by lambda x plus lambda y. So if you don't remember, we just did the calculations here. You can follow the same way. So the results will be, the total results will be 1 minus lambda y divided by lambda x plus lambda y. Okay, and that is equal to lambda x divided by lambda x plus lambda y, right? So that's why the results show us we get the same results even if we think from the different angles. You can think to create the rectangular for like that one or that one, and the logic actually the same. I mean, in one way you will fix the x values, in another way you will fix the y values, okay? But you will get the same result, which is the lambda x divided by lambda x plus lambda y. The important point is here, if you are asked what is the probability of the one exponential random variable is less than another exponential random variables, they are independent. The results should be the rate of one random variables that should be less than, or that should be less than another one, is divided by the total rate. Okay, if you are asked the probability of x is less than y, the results should be the rate of x divided by rate of x plus rate of y. Okay, so another exercise, to let x and y be independent exponential random variables with the parameters lambda x and lambda y. And the questions now, what is the distribution of z, and z is equal to minimum of x and y. So how can we do that? How can we find that one? Okay, so the CDF of z, which is equal to probability of z is less than or equal to some particular values, right? The CDF shows this kind of information. And also, this one is equal to 1 minus p, the probability of z is greater than z, some particular values, okay? So that is the same thing. Okay, so what is the z? Z is minimum of x and y, right? So I can rewrite this part as 1 minus probability of a minimum of x and y should be greater than z. So I can also rewrite that one. If the minimum of these two guys is greater than z, that means the x and y, both of them should be greater than z, right? So I can rewrite this part as this one, the 1 minus probability of x is greater than z and y is greater than z. We know that the x and y is independent random variables, right? And we learned that the probability of x and y, which is equal to the product of probability of x and probability of y, right? So here I use the power of the independence. Okay, that is independent. Okay, independent. That is coming from the independent rules. That's why I can rewrite that guy as 1 minus probability of x is greater than z times probability of y is greater than z, right? Okay. What is this? We know that x is exponential, right? And I know that the CDF of the exponential random variables is 1 minus e to the minus lambda x, right? And that guy show me the probability of x is less than or equal to some other one, some particular values. If I care about the probability of x is greater than some particular values, what I need to do is 1 minus this guy, the CDF, right? E to the minus lambda x. And that will give me 1 minus 1 plus e to the minus lambda x. These two guys will cancel each other. And if I am working with an exponential random variables, and if I am asked the probability of x is greater than some particular values, I can use that one, e to the minus lambda x. Okay. So here we have the same thing, probability of x will be greater than some particular values. That's why I can use this guy, so which is e to the minus lambda xz times e to the minus lambda yz, and I have one here. So I can rewrite that guy as 1 minus e to the minus lambda x plus lambda yz. Okay, so what is that? That is the CDF of the exponential distribution with that is the CDF of an exponential random variables with the rate lambda x plus lambda y, right? Remember that. Well, let me write here. The CDF is 1 minus e to the minus lambda x. That is the CDF of the exponential distribution. So instead of lambda, just put lambda x plus lambda y. Okay, so I can say that the z is the exponential with the rate lambda x plus lambda y. So if you have any questions such that you have two exponential distributions, two exponential random variables, they are independent, and you have been asked a new let's say, function like z, and that is represent the minimum of that two exponential distributions, or that is the minimum of that two exponential random variables, you can safely say that the z is exponential random variable with the rate lambda x plus lambda y. Okay, that is an useful property of the exponential, independent exponential random variables. That is the valid for the under the case of independence. If they are not independent, I cannot say something like that. Okay, please follow what I did and make sure you understand better. You don't need to memorize that the calculations, but please just try to remember this kind of piece of information that will be useful in your future classes. Okay, so that is the end of part 5, and I will see you in next part.